A fighter jet can carry advanced electronics, fly at enormous speed, and cost a fortune to build. But when it is sitting on the ground, it may still depend on one long strip of concrete. During the Cold War, that dependence began to look like a problem worth solving. Britain started asking an unusual question. What if a military jet could operate without depending entirely on a conventional runway? The answer would eventually become the Harrier. Today, the aircraft is remembered for one thing above almost everything else: hovering. Images of a jet hanging almost motionless above the ground made the Harrier instantly recognizable. It looked less like a conventional fighter and more like something aviation engineers had pulled out of science fiction. But the hover was not really the point. The deeper idea was flexibility. To understand why Britain was willing to spend years solving the extremely difficult engineering problems behind vertical and short takeoff and landing, you have to look at what was happening to military aviation after the Second World War. Jet aircraft were becoming faster, heavier, and more capable, but those improvements came with increasing dependence on prepared airfields, long runways, fuel installations, maintenance facilities, ground equipment, road and rail connections. The aircraft might be mobile in the air, but the infrastructure supporting it was not. And during the Cold War, planners across NATO had reason to think carefully about that dependence. A major air base was a large, fixed piece of infrastructure. It could not simply be moved because the strategic situation changed. A modern fighter might be able to relocate quickly, but only if another suitable airfield was available. The runway had become part of the vulnerability equation. This did not mean conventional air bases were suddenly useless. They remained essential to military aviation. But it did raise a question. Could some combat aircraft become less dependent on them? Britain was well positioned to explore that idea. The country already had a strong aerospace industry, experienced aircraft designers, engine manufacturers, military test organizations, and decades of experience turning unconventional ideas into flying machines. At Hawker, a small team began working on a concept that would eventually become the P-1127. At the same time, engineers working on propulsion were developing what would become the Pegasus engine. That relationship is one of the most important parts of the Harrier story. The aircraft and the engine were not two separate ideas that happened to meet later. They had to evolve together. A conventional jet engine produces thrust primarily to push an aircraft forward. The Pegasus concept allowed thrust to be redirected in a way that could support vertical and short field operation. That sounds simple when reduced to one sentence. Engineering it was anything but simple. A jet aircraft still had to behave like an airplane once it was moving forward. It needed to carry fuel. It needed usable internal volume. It needed structural strength. It needed flight controls that worked across very different operating conditions. It needed an engine powerful enough to make the concept practical without making the aircraft so heavy that the original advantage disappeared. And all of those things had to fit into one machine. A radical aircraft is rarely created by one radical idea. It usually comes from hundreds of ordinary engineering problems being solved one at a time. That was the reality behind the P-1127. The pilot would eventually make the hover visible. The engineers had to make the hover possible. By the end of the 1950s, the basic concept was moving out of the drawing office and toward hardware. Engine development progressed. Prototype construction followed. And by 1960, Hawker was ready to answer the first major question. Could the aircraft actually lift itself? On October 21, 1960, the P.1127 began tethered hovering trials. The aircraft was restrained while engineers examined the basic behavior of the new design. That was an important milestone, but it was still a very controlled experiment. Less than a month later, on November 19th, the P-1127 made its first untethered hover. For the people who had spent years working through drawings, engine tests, structural calculations, and prototype construction, the idea was finally hanging in the air under its own power. But hovering proved only one thing. It did not prove Britain had a useful military airplane. A machine capable of rising vertically from the ground might be technically impressive, but unless it could also perform efficiently as a conventional aircraft, its military value would remain limited. That became the next problem. On March 13, 1961, the P-1.7 made its first conventional flight. During that year, testing also demonstrated the ability to transition between vertical and conventional flight. That was a fundamentally different achievement from simply hovering. A hovering machine could remain an experiment. An aircraft capable of moving between vertical lift and normal forward flight began to look like something that might actually become operational. The development team had crossed an important line, but another problem remained. Proving that an aircraft could fly was not the same as proving that a military organization could use it. Military aircraft do not exist alone. They exist inside systems. Pilots have to train on them. Ground crews have to maintain them. Spare parts have to be supplied. Engines have to be serviced. Fuel has to reach the aircraft. Units have to understand what the new capability actually gives them and what new problems it creates. This distinction would shape the next stage of the program. The P.127 was a development aircraft. It was not yet the Harrier the world would later recognize. The next major step was the Kestrel. The Kestrel developed the basic concept further and allowed the idea to be evaluated under conditions closer to military service. By this point, something interesting had happened. Britain was no longer the only country paying attention. The United States and West Germany had also become interested in understanding whether VTOL aircraft could provide useful military flexibility. A tripartite evaluation squadron was created with British, American, and West German participation. 9 Kestrels were used in the evaluation program. This was significant for reasons beyond the number of aircraft involved. Britain had begun with an unusual national experiment. Now pilots and military organizations from 3 NATO countries wanted to know whether the concept actually worked. Once American and West German pilots were evaluating the Kestrel alongside the British, the idea was no longer simply a hawker curiosity. The evaluation during the mid-1960s examined whether VTOL could move beyond demonstration flying and become something military units could realistically support. That was a much harder test than simply proving an aircraft could hover for a photographer. Could pilots adapt to it? Could ground organizations support it? Could the aircraft perform useful military tasks while retaining the flexibility that made the entire concept attractive in the first place? These questions mattered because STOL was not free. Every aircraft design is a trade-off. If engineers give an airplane a capability that conventional aircraft do not have, something else usually becomes more difficult. Solving the runway problem did not remove complexity. It moved some of that complexity into the aircraft. The propulsion system had to do more. The airframe had to accommodate different operating demands. Designers had to balance vertical or short-field capability against the same kinds of constraints every military aircraft faces: weight, fuel, structure, reliability, maintenance, and useful performance. Less infrastructure outside the aircraft required more engineering inside it, and Britain was discovering that not every possible STOL path would survive. During this period, another British project, the P-1154, explored a more ambitious supersonic STOL direction. It did not become an operational aircraft. That failure matters because the history of the Harrier can look much cleaner in hindsight than it actually was. It is easy to draw a straight line from P-1127 to Kestrel to Harrier and imagine that success was inevitable. It was not. Britain experimented. Some ideas survived. Others did not. Requirements changed. Programs competed for money. Engineers learned which combinations of ambition and practicality could actually be turned into service aircraft. The Harrier emerged from that process. By the second half of the 1960s, the central question had changed again. The concept had flown. It had transitioned between vertical and conventional flight. International pilots had evaluated it. Now Britain had to decide whether it could turn the idea into a production aircraft. On December 28, 1967, the first production Harrier GR.1 made its first flight. The strange experimental aircraft of the beginning of the decade was becoming something very different, a military product. And in July 1969, the Harrier GR.1 entered frontline RAF squadron service with No. 1 Squadron. Less than a decade had passed since the P.127's first tethered hover. That is a remarkable development timeline when you consider what Britain had actually accomplished. In 1960, engineers were still proving that the concept could lift itself safely. By 1969, the Royal Air Force had formed an operational squadron around the basic idea. The experiment had become a capability. And this is where the original Cold War purpose becomes much easier to see. The Harrier was not valuable simply because it could hover. It was valuable because STOL gave the RAF more choices about where aircraft could operate. Britain began integrating Harriers into its Cold War force structure, including deployments connected with RAF Germany. The idea was not that Harriers would somehow operate without support. They still needed fuel. They still needed maintenance. They still needed spare parts. They still needed trained crews. They still needed logistics. But they did not have to depend in exactly the same way on a long, permanent conventional runway. That distinction is everything. The Harrier did not eliminate infrastructure. It changed the relationship between aircraft and infrastructure. A conventional airfield concentrated many requirements in one fixed location. The Harrier gave planners the possibility of dispersing some aviation activity away from the traditional model of a large runway-centered base. That flexibility was particularly attractive in the Cold War environment. And now the famous hover begins to look different. For the public, hovering was spectacular. For the RAF, the more important question was what that capability allowed the service to do differently. The hover was the spectacle. Flexibility was the purpose. There was also an important practical distinction between what the aircraft could technically do and how it was normally most useful. The Harrier was capable of vertical operation, but that did not mean every takeoff had to be vertical. A short takeoff could often allow the aircraft to operate more efficiently when carrying a heavier load. That is another reason the phrase, "a fighter that never needed a runway," can be misleading. The Harrier was not about proving that concrete was obsolete. It was about reducing dependence on the long prepared runways required by conventional fast jets. That is a much more important achievement, because military engineering is rarely about eliminating every constraint. More often, it is about giving commanders and organizations another option. And the Harrier gave Britain an option that few other operational combat aircraft could offer. But the story did not remain confined to the Royal Air Force. The same basic idea that made Harrier attractive on land also created possibilities at sea. The Royal Navy had its own problem. Carrier aviation traditionally depended on large flight decks and systems designed around conventional takeoff and landing aircraft. A STOL aircraft changed that equation. If an aircraft did not require the same runway length as a conventional naval fighter, then smaller flight decks could become much more useful. That helped open the path toward the Sea Harrier. Again, the underlying technology was being asked to solve a different infrastructure problem. On land, the question had been how to reduce dependence on conventional airfields. At sea, the question became how to operate capable fixed-wing aircraft from ships that did not resemble the enormous conventional carriers used by the United States. The answer was not identical, but the same STOL concept had suddenly found another reason to exist. This is one of the most interesting things about successful engineering ideas. They are sometimes developed for one problem and later prove useful for another. By the end of the 1970s, Sea Harrier had brought the concept firmly into Royal Navy aviation. And then, in 1982, history placed British STOL aircraft into a situation very different from the Cold War scenario that had helped create the original Harrier requirement. The Falklands conflict unfolded thousands of miles from Britain. The geography alone created enormous logistical challenges. British forces had to operate across the South Atlantic, far from the country's normal military infrastructure. Royal Navy Sea Harriers operated from HMS Hermes and HMS Invincible, RAF Harrier GR. 3 aircraft were also deployed to the South Atlantic. The Falklands did not explain why the Harrier had been created. The aircraft was already more than a decade into RAF service before the conflict began. Sea Harrier development had also started long before 1982. But the conflict did demonstrate something important about the philosophy behind the aircraft. Operating flexibility mattered. That does not mean the Harrier solved every problem. It did not make logistics disappear. It did not make ships unnecessary. It did not eliminate maintenance. And it did not suddenly make geography irrelevant. Quite the opposite. The South Atlantic showed how demanding geography could be. What the Harrier offered was another way of working within those constraints. A capability originally associated with Cold War dispersal and reduced runway dependence had found relevance in an environment where conventional airfield infrastructure was extremely limited. That is why the Falklands belong in the Harrier story. Not because Britain had secretly designed the aircraft for a war that would not happen until decades later, and not because the conflict proved that STOL was automatically superior to every conventional aircraft. It belongs because it showed, very publicly, why flexibility could matter. By then, the image of the Harrier had become inseparable from vertical flight. For television cameras, it was perfect. A jet hovering above a runway looked impossible. A fighter lowering itself toward a ship seemed to violate the normal rules of fast jet aviation. That visual identity was so powerful that it sometimes obscured the engineering logic underneath it. But go back to the beginning. Before the Harrier, before Kestrel, before Pete 1127 had even left the ground, the central problem was not how to make an airplane perform an impressive trick. The problem was dependence. Conventional jet aviation had become tied to large airfields. Britain wanted another option. Hawker's designers and the engineers behind Pegasus spent years turning that requirement into hardware. First, they had to prove that the aircraft could lift itself. Then, that it could fly conventionally. Then that it could transition between the two. Then that pilots from multiple countries could evaluate the concept. Then that a production aircraft could be built. Then that the RAF could actually organize a squadron around it. Each stage answered one question and created another. That is how real engineering programs work. There was no single moment when someone invented the Harrier fully formed. The aircraft emerged through accumulated decisions. Some were successful. Some led nowhere. Some required compromise. And the final design was not perfect because no aircraft is perfect. The important question is whether the trade-offs make sense for the problem being solved. For Britain during the Cold War, the answer was yes, often enough to take the idea from an experimental prototype to frontline service. And that says something broader about military technology. It is easy to judge an aircraft by the things that are easiest to photograph: speed, size, weapons, noise, a dramatic maneuver. But those visible qualities do not always explain why the machine exists. Sometimes the most important feature is the relationship between the machine and everything around it. The Harrier changed that relationship. It allowed Britain to think differently about the ground beneath a combat aircraft. The runway was no longer an absolute requirement in the same way. That did not make conventional runways obsolete. It created flexibility where previously there had been less. And flexibility has its own value. The aircraft could be supported in ways conventional fighters could not. The same concept later became useful aboard British ships. And when circumstances changed, the capability found roles its original designers could not have predicted in detail decades earlier. That is a much more interesting story than simply saying Britain built a jet that could hover, because the hover itself was only the visible result of a much deeper engineering decision. Less infrastructure outside the aircraft required more engineering inside it. That trade-off shaped the P.127. It shaped the Kestrel. It shaped the Harrier. And it explains both the aircraft's strengths and the compromises Britain was willing to accept. The Harrier makes the most sense when you stop asking how Britain made a fighter hover and start asking why Britain wanted a fighter that could operate without depending on a conventional runway. Once you ask that question, the entire development story looks different. The early experiments make more sense. Pegasus makes more sense. The Kestrel evaluation makes more sense. RAF Germany makes more sense. Sea Harrier makes more sense. And even the aircraft's later history in the South Atlantic becomes part of the same larger idea. The hover was the spectacle. Flexibility was the purpose. So here's the bigger question. Was the Harrier worth the engineering compromises required to reduce its dependence on conventional runways? Or did the complexity of STOL create too many trade-offs for the flexibility it provided? Britain spent years turning a strange experimental idea into an operational aircraft, and the result became one of the most recognizable jets of the Cold War. Tell me what you think in the comments, and if you enjoy fact-based stories about the decisions, engineering, failures, and history behind the world's most unusual military systems, subscribe to Defense TV, because sometimes the most memorable feature of a weapon is not the real reason it was built.